So I'm gonna get started. The last set of worksheets and the last homework are due on the second. That'll be after Thanksgiving. Exam number 4 on chapters 23 and 29 will also be on the second. Your presentations and your papers are due on the 4th, and you need to get them done like before class on the 4th, because you may be presenting on the 4th. So the due date on Brightspace is 8 AM. You need to write a 2 to 3 page paper on your topic and a 4 to 8 minute presentation on your topic. You're going to present your presentations in class. The schedule of presentations is up on Brightspace. So if you go to the semester project section, there's a schedule of presentations here. It lists the order in which everyone is going and the date they're scheduled for. So if you make sure to submit your presentation as PowerPoint slides, I'll be able to pull them up and you submit, before the due date, and I'll be able to download them and pull them up. Or if you bring them on like a USB stick or something, I'll be able to put them up during the presentation. So you submit them in a format that can be opened easily on a computer here, then you can do your presentation without any issues. And you all have access to PowerPoint through the online version of Office via City Colleges, so you can all use PowerPoint. But you should be able to, I don't know, most things. I mean, if you end up just exporting your presentation as like a PDF, that also works. You can step through the pages. But yeah, that's what I'm looking for. So make sure your presentation is submitted by the 4th, so I can pull it up. And if there's time at the end on the first day, and someone wants to do their presentation early, I'm okay with that. But the schedule is when you're supposed to do it, and that was literally random. The presentations will be in class, and so make sure your slides are ready. So we were discussing active galaxies and quasars. So the two primary differences between normal galaxies and active galaxies is active galaxies are much more luminous, and active galaxies emit radiation in a pattern that doesn't match the normal black body spectrum you see from stars and such. It's more non-stellar radiation. And the source of all this additional light and non-stellar radiation is the active galactic nucleus. And it's the activity in the nucleus of a galaxy that makes it active. So an active galaxy has an active, is defined by active galactic nuclei. Those are what powers them. So about 20 to 25% of galaxies don't fit well into the Hubble scheme. They're far too luminous. They're too bright. And these galaxies are called active galaxies. They differ from normal galaxies both in how bright they are. So you see how the active galaxy has much more intense light, and the type of radiation they emit. So this is what a normal galaxy looks like. It's more or less a black body spectrum. The active galaxy is much flatter. So it both has a lot more radio and a lot more X-ray. It's called non-stellar radiation. And many luminous galaxies are experiencing an outburst of star formation, probably due to interactions with a neighbor, and these are called starburst galaxies. But galaxies that are undergoing events occurring in and around the galactic center is what we're discussing here. So a Seyfert galaxy is a spiral galaxy with an unusually bright nucleus. So it's a spiral galaxy who has an active galactic nucleus. So here's another image. There's a few different types of active galaxies: safer galaxies, radio galaxies, quasars, blazars. So safer galaxies look like normal spiral galaxies, but the cores are thousands of times more luminous. Make sure to sign in. And the rapid variations in the luminosity of safer galaxies indicate that the core needs to be extremely compact. So you can figure out the size of something that's emitting light by looking at, you can put an upper bound on the size of something emitting light by looking at how it varies. Because if something is varying rapidly, well, it can't be too big, because otherwise changes, light from the far side and light from the near side would take a longer amount of, different amounts of time to reach you. And so that would sort of even out any variations on time scale. So that's one of the ways we can figure out the scale of these things. Radio galaxies emit excess radio emission. They often have huge jets of material that can be seen emitting from these radio galaxies. So radio galaxies emit very strongly in the radio portion of the spectrum. They can have these enormous lobes that are jets of material that are visible to optical telescopes, but show up in radio waves, and they're perpendicular to the plane of the galaxy. So you have a spinning galaxy, and the jets shooting out of the top and bottom of that disk. They can also be core dominated. It's likely that a core dominated radio galaxy is just one where the jets are coming at us. Core dominated radio lobe galaxies are probably the same phenomenon viewed from different angles. Lots of active galaxies have jets, and most also show signs of interactions with other galaxies. So lots of these active galaxies are spewing out these jets of material, and many of them also show signs that they've interacted with other nearby galaxies. And blazars are the compact centers of elliptical galaxies that are incredibly bright, because something is actively occurring in the center of that elliptical galaxy. A quasar is a quasi-stellar radio source. It was one of the first things that was detected. They looked like star-like objects that were emitting radio waves, but they were weird because their spectrum didn't make sense. They were mysterious objects because the spectral lines didn't match with anything that was done on Earth. In 1963, Martin Schmidt noted the emission lines of the spectrum of quasar 3C273 had the same spacing as hydrogen lines, but were extremely redshifted. By his calculations, 3C273 was receding at 15% of the speed of light. And with that big of a redshift, Hubble's law tells us that it needs to be very, very far away. So quasars, quasi-stellar objects, are star-like in appearance. This is quasar 2C273. And here's a relativistic jet that's produced by its central black hole. But they have very unusual spectral lines. So you can see here, this is sort of a lab comparison spectrum. These are the lines in question. You can see the enormous redshift here. These lines are shifted from like being greenish down to almost, being, actually no, from like blue, the sort of bluish or greenish into the red. It's a really big redshift. And the highly redshifted spectra of quasars indicate enormous distances. And then, so because of the redshift, we can figure out the distance. We can observe the brightness, and then we can work out how luminous it needs to be. And we find the luminosities of these are something like 10 to the 12 times the luminosity of the sun. more than 10 to the 12 times the luminosity of the sun. And the fact the variations of these quasars are fast enough to show that all this energy is coming from a region smaller than the solar system. So they're star-like only because they're very, very far away. They're actually the nucleus of a distant galaxy. We now know about millions of quasars. All observed quasars have large redshifts. The largest velocities are around 96% of the speed of light. Basically, all the quasars we look at are moving very fast away from us, which means they're very far away. The evidence looks like quasars are very much something that happened in the early universe and aren't happening anymore. So this is the first object that was identified as the quasar that has a luminosity 1 trillion times that of the sun. So quasars are parts of galaxies. They're the cores of galaxies. Because galaxies obey Hubble's law, so should quasars. Pretty much all of them are 10 billion or more light years away. None of them are nearby. What that means, since we see them in all directions, what that means is really that they were something that happened earlier in the history of the universe, and the processes that formed these have ended. So there may be some things that used to be quasars sitting around, we don't know, nearby. That's actually pretty reasonable as a thought. But what we were seeing is we're seeing some part of the early history of the universe, and the remnants of these quasars, once they ran out of the fuel that made them so bright, are just regular galaxies now. So when we solved the spectral problem, we figured out the spectrum, we then realized they're so far away, they have to be some of the most luminous objects in the universe to be visible over such enormous distances. They're incredibly bright. So let's talk about the evidence for the supermassive black holes at the centers of the galaxies. One of the things you could do is that you could get an estimate, you can get an upper bound for the size of an energy source by looking at how it varies with time. So an object can't vary in brightness faster than the time it takes for light to travel across it. Because if it, let's say you had some object, it suddenly doubles in brightness. But it's a light year across. The increase in brightness from the front, you'll see right away, but the far side will take a year to reach you. So the length, the size of an object, so if you have an object 10 light years across, we'll first see a bright increase in brightness from the near side. 5 years later, we'll see an increase in brightness from the center, and then 5 years later, we'll see an increase in brightness from the far side. Even if they all instantly increase. So the variations we see give you some sort of upper bound on the size of an object. Lower bound. Yeah, upper bound. You get a maximum size they can be. Quasars, very, very quickly, months or even weeks. And because of this, the energy source has to be small. It can't be much larger than a solar system. Things varying on the order of months or even weeks, that's small. Now, what is the energy source of quasars? Quasars and other active galaxies all have the same energy source. That energy source is the supermassive black hole at the center of the galaxy. And specifically, the energy source is the accretion disk around that black hole. So the accretion disk around a black hole, as matter falls into the black hole, can give us tremendous amounts of energy. So friction and as matter falls in, gravity increases its energy, and then friction causes it to heat up. and it could pump out enormous quantities of energy. And this is the only explanation we have for such a large amount of energy coming from such a small volume of space. We also know there are supermassive black holes in the center of galaxies in much more detail than we used to because we've taken pictures of them. So active galaxies differ from ordinary galaxies in that they emit more energy and emit a different type of energy than an ordinary galaxy. Quasars are an important type of active galaxy and were determined to be the cores of distant galaxies. And the energy source of an active galaxy is a supermassive black hole at its center. So let's talk about what powers an active galactic nucleus. So some of the properties of quasars and other active galactic nucleus, they're extremely light luminous. These nuclei are brighter than the entire galaxy they're in. They're very small. They're about the size of our solar system. They emit jets of material in a narrow beam at nearly the speed of light. This much energy emitted from such a small region needs an energy source much more powerful than nuclear fusion. Like nuclear fusion is not powerful enough to generate energy at the level that we're seeing in an active galactic nucleus. And quasars were much more common in the early history of the universe than they are today. So again, they have high luminosity, non-stellar energy emission, variable energy output indicating a small nucleus, jets and other signs of explosive activity, and broad emission lines indicating rapid rotation. So there's some going around real fast that's pumping out huge amounts of energy in a manner that isn't just stellar, it isn't heat. And they're small. So the leading theory is the energy source for an active galactic nucleus is a supermassive black hole and the accretion disk of material falling into it. So as material falls into the supermassive black hole, it interacts with other material, it accelerates charged particles. Particles get ionized and they accelerate around the black hole. That causes them to emit light. The strong magnetic field lines around the black hole channel particles out to form the jets, and lots of friction generates energy and such in the accretion disk as things orbit around. But the charged particles accelerating around in the orbits give you synchrotron radiation, which will give you that non-stellar radiation. So this is galaxy M87. This is actually the galaxy we image the first supermassive black hole at the center of. And it's an active galaxy relatively close to us. It's a quasar, I believe. It's a large elliptical galaxy.
M87 is an elliptical galaxy with an active nucleus. An active nucleus is at the center of the galaxy, and a jet of particles is being emitted from it. On zooming in, a disk of gas present in the nucleus can be observed.
So, and to extension, we've now imaged the actual black hole at the center. So the Event Horizon Telescope imaged the supermassive black hole at the center of M87. It's measured to be around 6 billion solar masses. This circle here is the size of Pluto's orbit, just for scale. So the black hole's in the center, you're looking at the accretion disk, but because it's a black hole, you're also seeing behind the black hole as light is bent around it. So you see the front and the back. But yeah, so this is M87, the core of M87, it's around 6 billion solar masses. So how do you get energy from the black hole? Well, obviously you're not getting it out of the hole itself. But the gravitational potential energy of matter falling into a black hole turns into kinetic energy as stuff speeds up as it falls into the black hole. And friction in the accretion disk turns that kinetic energy into thermal energy, and that produces heat, which produces thermal radiation, photons. And this whole process is violent friction, collision, and such around a black hole can actually convert 10 to 40% of the mass into energy, into radiation. It's one of the most effective methods of converting matter into radiation that we know of out there. So it's quite impressive. It's incredibly violent, tearing stuff apart and generating all kinds of radiation. So in an active galaxy, the central black hole can be billions of solar masses. M87 is about 6 billion solar masses, for example. And the accretion disk is entire clouds of interstellar gas and dust, and they can radiate away as much as 10 to 20% of their mass before disappearing into the black hole. So this is, fusion converts about like a fraction of the mass. It's less than 1%. This is 10 to 20%. It's one of the most effective ways to convert mass into energy. So here's some observational evidence for supermassive black holes. So indirect evidence, there's a large mass and a small volume. We see short time period variations in brightness. So how can we determine the mass of these objects? Well, we can use Kepler's third law. We have various objects orbiting this massive thing. The orbits of stars near the galactic center in the Milky Way was used to determine the central mass in the Milky Way is about 4.1 million solar masses, and the size is about the diameter of the orbit of Neptune. In M87, we can determine it by looking at the motions of gas around the center for an elliptical gas. So we look at various things orbiting the center, the black hole in question. So here in M87, we can look at the spectrum of the gas disk in M87. We can see it, approaching and receding on other opposite sides of the core. So this side is approaching, this side is receding, the whole thing's spinning around, and we can get the speeds from the redshifts. So how can a black hole produce energy? Because nothing can escape from a black hole. Well, that energy is produced in the accretion disk. It's produced outside the black hole. As material falls into a black hole, the gas accelerates to high speeds. It heats through friction to something like 100,000 Kelvin. And then it starts to tear itself apart and can convert 10% or more of its mass to energy, while nuclear fusion in a star converts less than 1%. And this emits several types of radiation. It emits light from heat, but it also, because these particles ionize, they're so hot they're ionized. They're charged particles orbiting around a black hole. Anything orbiting is accelerating. Any accelerating charged particle will emit electromagnetic radiation. So they emit lots of radio waves because of the way they're orbiting around. The jets of material emerging from an active galaxy can be very spectacular. As you can see, here are these jets. Here's the active galactic nucleus. So these radio jets are caused by basically the accretion disk as it builds up, sort of squeezes material in, and you get material shot out the top and bottom of the accretion disk. So large amounts of material are spiraling in. These intense pressures fling material outwards. But since there's more material in the disk, it gets pushed perpendicular to the disk. And you get these jets of material shooting out the top and bottom. Also, because everything is charged, they sort of follow magnetic field lines coming out the top and bottom of the black hole. And observations of active galactic nuclei show this type of outflow. These jets of material are actually quite common. So here are some examples of actual jets from active galaxies. There's the active galaxy. Here's that relativistic jet. And you might expect the radiation to be mostly X-rays and gamma rays because it's so hot. But apparently it gets reprocessed in dense clouds around the black hole and re-emitted as longer wavelengths. So that spreads out the radiation. Additionally, particles emit synchrotron radiation as they spiral along the magnetic field lines. And synchrotron radiation is non-thermal, mostly in radio waves, less at higher frequencies. This purple line is thermal radiation, the blue line is what synchrotron radiation looks like. When you combine them, you get something a lot flatter. So one of the nice things about quasars is that quasars let us probe the early universe. So if we see a quasar 10 million light years away, that's seen as it was 10 billion years ago. So what does it look like today? Well, it's probably now just a regular looking galaxy. And the number of quasars has decreased over time, as you can see on this chart. And it seems like the last quasars were something like 10 billion years into the history of the universe. So before the Earth even existed, kind of scale. So basically long ago, quasars had fuel for their engines. They no longer do. Probably just all got used up. So there were massive clouds that could fall into galactic nuclei. The conditions that create quasars just don't happen anymore. And the black holes that power quasars are still here today. They're just not pumping out trillions of times the luminosity of the sun anymore. They're a lot more quiescent. So what are the sources of fuel for active galactic nuclei? Well, occasional passing stars or gas clouds get pulled in and consumed. A star can be torn apart by tidal forces. And this larger, brighter periods can be triggered by collisions. Colliding galaxies cause disturbances and movement of the material within the galaxies. So that can cause much larger gas clouds to feed into the black hole. And these collisions between galaxies were much more frequent in the past. So it's likely that active galactic nuclei were more common when collisions were more common, which fed into disruptions of the structure of galaxies feeding these black holes. So here are images of distant galaxies. You can see all these collisions. They were much more common in the past. So lots of galaxies colliding with each other here. And so one of the questions you might ask is, do these supermassive black holes regulate the evolution of galaxies? Well, how do galaxies evolve? We know it's not along the Hubble tuning fork, but one of the things we do know is that many nearby galaxies, perhaps all of them, it seems like most of them, have supermassive black holes at the center. These seem to basically be dormant active galactic nuclei. Any one of them, if you gave it enough material, could be an active galactic nuclei. So our galaxies may have passed through some sort of quasar-like stage earlier in time. Maybe. And then again, maybe not all of them quite do. This is still a field of active study, and we still don't fully understand how galaxies. We do know that the mass of a galaxy's central black hole is closely related to the mass of its bulge. So galaxies with large bulges have larger black holes, while those with smaller bulges have smaller black holes. And the development of therefore, the development of a central black hole must somehow be related to the evolution of galaxies, because it's clearly tied to the structure of galaxies. So active galaxies are powered by the supermassive black hole at their core. We can infer their existence because of the amount of energy being produced from such a small area and the motions of stars in the center. And studying quasars tells us about the early history of the universe, since this is when they were most active and most common. Turns out another thing that quasars are useful for is because they're so far away, their light has passed through a lot of the universe on the way to us, so their absorption spectrums are actually very interesting to study. So this is the end of the chapter. So the Hubble classification organizes galaxies according to shape. The galaxy types include spiral, barred spiral, elliptical, and irregular. Objects of relatively uniform luminosities are called standard candles. Some examples are RR Lyrae stars and type 1A supernovae. Those are the most commonly used for very distant galaxies. The Milky Way lies within a small cluster of galaxies called the local group. Other galaxies clusters may contain thousands. Hubble's law is that galaxies recede from us faster the further away they are. Active galaxies are far more luminous than normal galaxies, and their radiation is non-stellar. Safer galaxies, radio galaxies, and quasars all have very small cores, and many emit high-speed jets. And active galaxies are thought to contain supermassive black holes in their centers, where infalling matter converts to energy, powering the galaxy. And we've identified supermassive black holes in the centers of many galaxies. So that's the end of chapter 27. And now on to chapter 28. Share. So let's talk about galaxies and dark matter. So one of the things we've identified about galaxies is that there is clearly a lot more matter there than we can see. So let's talk about the evolution of galaxies and our understanding thereof. So when we look at distant galaxies, can we observe changes in them? So we know changes in galaxies, similar to stars, changes in galaxies occur over timescales that we can't actively observe. Galaxies don't change at all during the period of time that is a human lifetime. But because light travels at a finite speed, we can see galaxies throughout the history of the universe. A galaxy at a distance of 12 billion light years is seen as it was when the universe was only 2 billion years old. A galaxy at a distance of 2 billion light years is seen when the universe was like 11 billion, about 4 billion light years, is about seen when the universe is about 10 billion years old, that kind of thing. And this allows us to study the evolution of galaxies, because we can see how galaxies change over the history of the universe. Now, figuring out the spectrums of distant galaxies is actually quite hard because they're so faint. Because when you separate things out into a spectrum, if you're only getting a little bit of light from this galaxy, when you separate it into a spectrum, it's hard to figure out any detail. But we can observe the colors of galaxies. So, for example, blue galaxies must have had recent star formation. Red galaxies have not had recent star formation. We can also look at the early and we're starting to be able to look at spectra of galaxies. We look at early generations of stars. We find that heavy elements formed in the first billion years. In fact, we keep finding stars with heavy elements earlier and earlier than we expected. Like we found heavy elements formed fast, which means stars formed fast. And even very distant galaxies show lines of heavy elements that were not created in the Big Bang. And we keep being surprised by how early we see these. So that's one of the things that James Webb Space Telescope is trying to do, is see those stars from before heavy elements formed. Now, one of the things we see is that galaxies early in the history of the universe were colliding a lot, as you can see here. We now believe that the process by which galaxies evolve is due to mergers and interactions. This is the primary way that galaxies evolve over time. But you'll notice we talk about galaxies colliding and merging, but we don't really talk about stars colliding. Part of this is because galaxies are very large compared to the distances between them. But stars are quite small compared to the distances between them. So when two galaxies collide, the stars don't collide, but the galaxy structures themselves do. And many instances of galactic collisions have been observed. As you can see here are some impressive ones. So it's believed that the merger of smaller galaxies and star clusters plays a role in the formation of the galaxies we see today. Image C here shows some of the large star clusters found some 5,000 megaparsecs away. They may be precursors to a galaxy. So you may have had smaller galaxies and star clusters that merged to form larger galaxies. And we do know that larger galaxies will cannibalize smaller galaxies. We see that happening with the Milky Way. It's eaten several smaller galaxies and it's actively consuming some right now. This Hubble Deep Field view shows some extremely distant galaxies, and the most distant appear irregular, supporting this idea of galaxy formation by merger. So that Hubble structure, where you mostly see elliptical and spiral galaxies, falls apart when you start looking at really distant galaxies. Most of those are irregular because they're all colliding with each other. So what happens when galaxies collide? It's not like an ordinary collision. It takes hundreds of millions of years, and the individual stars don't collide. But all their orbits rearrange, the gas clouds collide, which enhances star formation. You get a starburst galaxy, and streams of material get ejected as the gravitational fields interact, and the shapes of the galaxies get distorted. So here we have some colliding galaxies. You can see lots of star formation, really odd shapes, material being sort of flung off. Because the separation between galaxies isn't very big compared to the size of the galaxies themselves, as you can see here, galactic collisions are actually quite frequent. And this cartwheel galaxy on the left appears to be the result of a head-on collision with another galaxy, possibly one of these two. So possibly what happened is this smaller galaxy splashed through this larger galaxy and created this sort of cartwheel structure. And this galaxy collision, where you can see these two galaxies colliding, led to bursts of star formation in both galaxies, and ultimately these will probably merge. And there's some dramatic colliding galaxies. There's like the antenna galaxies, which have two long streams generated by their collisions. Yeah. So the antenna galaxies collided fairly recently and are in the process of merging. They spark stellar formation. And you see these streams of material that are probably going to be, some of this material is probably going to be lost, and the galactic cores will merge. And one of the things we're trying to design are gravity wave detectors that can detect the mergers of these supermassive black holes. But we need to build even better and bigger gravity wave detectors. Each of these three starburst galaxies exists as massive star formation after a galactic collision. And in image A here, you can see the two colliding galaxies here and here. Well, it's not so clear in these. Another thing that happens is that friction causes colliding galaxies to merge. You get galactic cannibalism, where larger galaxies will cannibalize smaller galaxies, and similar sized galaxies will merge. So some galaxies show multiple nuclei from previous mergers, as you can see here. And galactic cannibalism, we even see that nearby. We see it happening with the Milky Way. Here we see an incidence of what appears to be galactic cannibalism. Dozens of small galaxies in the process of merging together. And we've identified streams of stars in the halo of the Milky Way that appear to be from smaller galaxies the Milky Way has cannibalized. So collisions are quite rare today, about 5% of galaxies, but they were much more common in the past. Distant galaxy clusters show multiple collisions. And galaxies are built up from the small galaxies that existed long ago to the larger ones we see today. Galaxies have collided and merged and formed bigger galaxies. So here is how, this is a simulation showing how maybe the interaction between a smaller galaxy and a larger galaxy could turn that into a spiral galaxy, sort of spin it up. And collisions can feed the black hole at the center of the galaxy because those colliding clouds of glass can get pushed towards the center and feed into the nucleus. This can cause a galaxy's nucleus or black hole to become an active galactic nucleus. We see active galactic nuclei were much more common in the early universe, at the same time when collisions were more common. And the formation of an active galactic nucleus core in jets may impact the process of star formation in the remainder of the galaxy. Again, it's a field of active study, and we're not fully sure. Here are some visible and X-ray images of supermassive black holes orbiting each other at a distance of about 1 kiloparsec, and they're expected to merge in about 400 million years. So these are two galaxies merging. The black holes are orbiting each other, heading towards each other, and will eventually merge. This galaxy viewed in this radio spectrum, mostly from 21 centimeter radio waves, and the Doppler shifts from the emission from the core show enormous speeds very close to the massive object, which is a black hole. So this is an active galaxy, possibly triggered by a collision. And careful measurements show that the mass of the central black hole of the galaxy is correlated with the size of the galactic core. These are spirals and ellipticals. The spirals are open circles, the ellipticals are empty circles. And there's sort of a fit line here. And the quasars we see are very distant. And that means they existed a long time ago, so they may represent a very early stage in galaxy development. So here are some quasars with their host galaxies. You can see the actual galaxy around the quasar, which is the super bright center. The super bright center is the quasar, then the faint disk around it is the galaxy. And the end of the quasar epoch seems to be about 10 billion years ago, and all of the quasars we see are mostly older than that. And the black holes powering the quasars don't go away. It's believed that many or not most galaxies have a supermassive black hole of their center. And this figure shows how galaxies may have evolved from early irregulars through active galaxies to the normal ellipticals and spirals we see today, where irregular galaxies merge, form a quasar, which could merge and form like a Seyfert, or become a normal spiral, or it could have some merger with another larger object, be a radio galaxy or a quasar, and become a normal elliptic. This sort of process. So galaxy revolution seems to be driven by collisions and galactic mergers and cannibalism. Galaxy collisions take a long time to occur, and the individual stars within the galaxy don't collide. And they were much more common in the early history of the universe and are relatively rare today. So let's talk about the cosmological principle. So how are galaxies distributed in space? Are they isolated? Are they in groups? Are these large or small groups? The cosmological principle is the way it's sort of an approach we can use to study the universe. With early observations by Hubble, noticed that there were about the same number, approximately the same number of galaxies in each direction. The cosmological principle is this idea that the universe is more or less isotropic and homogeneous. That means if you take a big chunk of the universe, you go to some other chunk of the universe, they will be more or less the same, and there is no special direction. If you look one way, it'll be the same as if you look some other direction. So the universe, it's isotropic. The universe looks more or less the same in all directions. And the universe is homogeneous. Every large volume of space looks essentially the same. There's no special direction. There's no special blob of space. So, if we look at our galaxy, our local cluster of galaxies. This is the local group. It contains 50 plus galaxies. And there are 3 large spiral galaxies and many dwarf ellipticals and irregulars. We're still discovering new members of our local group, generally small ellipticals and irregulars. These are being discovered by automated surveys, and these galaxies are quite faint, which is why they're they were predicted by these faint galaxies were predicted by formation models, but are only now being discovered because again they're quite faint, hard to see. But our local group is not a very big cluster. I mean, it's only 50 odd galaxies. There are much bigger clusters of galaxies as well. The Virgo cluster is the nearest large galaxy cluster. It's dominated by M87, which is a giant elliptical galaxy. The Virgo cluster contains thousands of galaxies. 3,000 to 4,000 galaxies, I believe. And it's about 50 million light years away. So this is the Virgo cluster. This is the Coma cluster, which is dominated by elliptical galaxies. It contains tens of thousands of galaxies, even bigger, and it's about 250 million light years. Now, one of the things we can look at is how galaxies are distributed within these clusters. And we find that elliptical galaxies are social galaxies. They tend to be clustered towards the center. They're found in the crowded centers of clusters. While spiral galaxies are shy. They hang out around the edges of these clusters. Now, what this probably means is that collisions destroy spiral galaxies. Spiral galaxies are probably less stable than elliptical galaxies. And collisions are less likely to happen around the edges of clusters. So the spiral galaxies that were in the center of clusters may have collided and stopped being spirals or been destroyed. So collisions are less likely to destroy spirals in the outskirts of clusters, which is why you tend to see them there, while the galaxies in the centers of clusters are more likely to be the spirals in the centers of clusters are more likely to be disrupted and become something more like an elliptical galaxy. Now, one of the ways we can look at the universe at very large scales is by studying the light from quasars. The quasars are all very distant. And the light coming to us from them has probably gone through lots of interesting places on the way here. Because it's gone a very long way, it's passed through lots of stuff. But one of the interesting things about that is that all of those places at different distances from us are going to have different redshifts. So we can separate them out in the spectrum of the quasars. So we can learn a lot about the intervening space between us and the quasar by looking at the quasar spectra. So by looking at all the little lines in the quasar spectra, so the absorption line forest in the quasar spectrum that you can see here, tons of light absorption lines, is the result of quasar light passing through hundreds of gas clouds, each with a different redshift on its way to reaching us. But that means if we look at different portions of the spectra, we can learn about different gas clouds at different distances from us. So we can analyze what's going on sort of by studying the spectrum of quasars and gas they fit through. Another interesting thing we see is things like this. This appears to be a double quasar. But when we pay attention to it, we notice these two quasars turn out to be not just similar, but identical. They in fact vary in luminosity at the same time. So what we're looking at here is not actually two quasars, but two images of one quasar. So what's happening is the light from this quasar is being bent around some massive gravitational object back towards us. And so we see multiple images of the same object. So this is an effect of gravitational lensing. So two images of the background galaxy formed by some unseen foreground gravitational lens. So the idea of this could occur via gravitational lensing. Gravity bends light. So if you have a quasar, you have light bent around one side of a foreground galaxy and bent around the other side, and you'll see two apparent images of the same object. So, and we can learn about the quasar itself, that there's usually a time difference between the two different paths. And we can learn about the lensing galaxy by analyzing how the light from the quasar gets bent. You can actually figure out like its mass and how that mass is distributed. So here, for example, the intervening galaxies has made 4 images of the distant quasar in blue, but these are all the same object. The light is being bent by the foreground. So this is gravitational lensing. It's a prediction of general relativity. Mass bends space-time and deviates light paths. We've observed it on a small scale with stars and the sun. And so what you would see is that you have a foreground galaxy and a background galaxy. And the more distant background galaxy, its images will be distorted when light passes through a cluster of galaxies. And that we could use to actually work out the mass that is generating that lensing. So the light from that object will be bent by the dark matter within a cluster of galaxies. So here are some spectacular images of gravitational lensing. You can see these bent arcs of galaxies behind, these multiple images of this blue galaxy. So on the left, these are distant galaxies being imaged by a whole cluster. On the right is a cluster with images of what is probably a single galaxy in multiple locations. The blue galaxy is what's being lensed. Here you can see several different galaxies being distorted and lensed by the cluster in front. So here we have a visible image of a whole cluster of galaxies. What you can do is use the lensing of distant background galaxies to work out where the dark matter is in a cluster of galaxies. And so you can build up an image of the distribution of dark matter in clusters of galaxies that help bind those clusters together. So here, for example, these are examples of gravitational lensing here. And the mass that causes this gravitational lensing includes dark matter that can't be seen. So it's one of the ways you can identify dark matter and figure out information about it. And we find that galaxy clusters join into larger groupings called superclusters. So this is a 3D map of the supercluster nearest us. This is our local group. These are the superclusters near us. This is the Virgo supercluster, which we're part of. There's some other superclusters. There's the Coma cluster up here. So we're part of the Virgo supercluster. And here are some of the individual galaxies within the Virgo supercluster. So here's the Virgo cluster, and this is the other parts of that. So clusters of galaxies will group into even larger structures, superclusters, and then there are these big gaps between superclusters that are voids. And this is the sort of largest scale structure of the universe. So this slice of the larger galactic survey shows the scale that on the scale of 100 to 200 megaparsecs, there is these structures in the universe, these walls and voids, but this seems to be the largest structure of the universe. Galaxies often cluster in these long filamentary structures that sort of resemble beads on a string. And when we map out the universe, this is sort of tricky because we need to determine distance to the various galaxies. This can be done with redshift surveys. We find that galaxies get concentrated into these filaments with empty voids in between. And we find about 90% of galaxies fill about 10% of the universe. So the biggest structures we think are things like the Sloan Great Wall, but above this scale, the universe is pretty similar. This is an even bigger survey, shows structure on the scale of 100 to 200 megaparsec, but there's no scale sign of structure on a larger scale than that. The apparent decreasing of density as we go away from the center is just due to the fact that it's harder to observe galaxies further away. So galaxies will group into clusters, and those clusters will group into superclusters and filaments. There are vast empty voids between the filaments, and the cosmological principle states the universe is both homogeneous and isotropic on the largest scales. So what we look at in astronomy is primarily ordinary matter. That's the stuff that will pump out light. This gives off electromagnetic energy. This is things like galaxies, stars, planets, etc. But there is dark matter in galaxies. About 90% of the mass in many galaxies is a dark matter halo. We can tell this from galaxy rotation curves, from starlight and 21 centimeter hydrogen. And dark matter exists in all galaxies to some extent. Lots of other galaxies have similar rotation curves to ours, allowing measurements of their mass. And this lets us determine that there's a large amount of dark matter in most galaxies. We can also identify dark matter in galaxy clusters. There's a couple ways we can do this. One, we can look at the motions of the galaxies. The galaxies in a cluster are all gravitationally bound. So there has to be enough mass to keep these galaxies from escaping the cluster and flying off. So you can figure out how massive a cluster needs to be. Additionally, you can use gravitational lensing. The gravitational field of the cluster will bend the light from more distant galaxies. You'll see multiple and distorted images of the distant galaxies, and you can work out the distribution of dark matter from them. Not easy, but it's possible. So one of the ways to measure the average mass of galaxies in a cluster is to calculate how much mass is required to keep the cluster gravitationally bound. Basically, thinking like Kepler's third law on the scale of galaxies. So you look at how fast galaxies are moving, and you can work out how much mass needs to be there to keep those galaxies from escaping. So here's some examples of gravitational lensing. And we can use this to figure out the distribution of the mass, the hidden mass in the galaxy cluster in front that is doing the lensing. And so how much dark matter is there? Well, when we look at mass to light ratio, the mass to light ratio for the sun is about 1. The mass to light ratio for galaxies is 10-ish. Small clusters have a mass to light ratio of around 100, large clusters around 300. Large ratios mean substantial amounts of dark matter must be present. Something like 80 to 90% of the matter is dark. So galaxy mass measurements are galaxies need between 3 and 10 times more mass than can be observed to explain their rotation curves. It's even larger in galaxy clusters between 10 to 100 times more mass. And the total needed is more than the sum of the dark matter associated with each galaxy. So there's extra dark matter holding the galaxy cluster. And there's evidence for intercluster superhot gas around 10 million Kelvin throughout clusters that's densest in their centers. But here's some examples of that. Here's this head-tail radio galaxy's lobes. They're being swept back, presumably because of collisions with intercluster hot gas. So these radio lobes from this are being swept back by hot gas coming from within. So this galaxy is moving through the background cluster glass. And it's believed that this gas is primordial, dates from the very early days of the universe, and there's not nearly enough of it to be the dark matter in galaxy clusters. So the real question is, what is dark matter made of? Well, one of the ideas is that it might be machos, massive compact halo objects. So this is stuff like black holes, brown dwarfs, white dwarfs, stuff that just doesn't emit light. That isn't visible directly, but you would see their gravitational effects. But our measurements show that there's not enough to account for the amount of dark matter needed in the halo of our galaxy, and we would notice them through things like gravitational lensing, because they would have very distinct gravitational lensing effects. So a more popular model is WIMPs, weakly interacting massive particles. So these are exotic particles that are quite heavy for subatomic particles, but only interact via the weak force. So they don't emit electromagnetic radiation. So they only interact via gravity and the weak force. And so that is something like that is the most commonly thought idea for dark matter. And one of the things we do know is that we can talk about hot or cold dark matter. Hot and cold refer to the speed of the particles. So one of the best possibilities for hot dark matter would be like neutrinos. So hot dark matter, though, would smear out clumps and inhibit the growth of clusters, while cold dark matter would grow clumps of matter, and that is the most consistent with our current observations. So simulations with cold dark matter end up matching the current structure we see of the universe. That's one of the ways we've actually eliminated neutrinos as a possibility for dark matter, because they would definitely be hot dark matter. It's one of the ways we know that the particles involved have to be massive. And I think I'm going to stop there for today. We will continue this on Thursday, and continue talking about the overall structure of the universe. So I'll see you all on Thursday. Stop sharing. End the meeting for all.